of bearing capacity of shallow footing using Terzaghi's theory. In this video, we'll see how the effect of water table is to be considered while estimating the bearing capacity of a footing using Terzaghi's theory. So to understand this, we'll take a problem. A strip footing 2 meter wide is placed at a depth of 1.2 meter in sand. The saturated unit weight of the sand is 19.5 kilonewton per meter cube, and the weight of the that is the unit weight of the sand above the water table is 16.8 kilonewton per meter cube. The shear strength parameters of the soil are C is 0 and angle of friction is 35 degree. So for the given condition, we have to find out the ultimate bearing capacity using Terzaghi's theory. The conditions are when the water table is 4 meter below the ground level. Second condition is water table is 1.2 meter below the ground level. Third condition is water table is 2.5 meter below the ground level. Fourth condition is water table is 0.5 meter below the ground level, and the last condition is water table ground level. We have to consider the value of NQ as 41.4 and N gamma as 42.4. Since again this is a sandy soil, the bearing capacity factor NC will not be considered. So we'll consider this case in which the water table is 4 meter below the ground level. So as per Terzaghi's theory, since again this is a case of strip footing, the equation for capacity is written as C into NC plus gamma into dF into NQ into RW1 plus 0.5 into gamma into B into N gamma into RW2, where RW1 and RW2 are the correction factors which is applied to the surcharge term and the wedge term. The middle term is known as the surcharge term and the last term is known as the wedge term. So once we have written the equation, we'll sketch the footing to understand whether the effect of the water table is to be considered or not. Now firstly we'll find out the correction factor RW1. So RW1 will be found out using the expression 0.5 into 1 plus ZW1 upon dF, where ZW1 is the depth of water table measured from ground level to the base of the footing. Now in this case, the water table is 4 meter below the ground level. Hence, the influence of water table won't be affecting the part of the soil above the base of footing. Hence, we'll take the value of RW1 as 1. Similarly, the second correction factor RW2 is found out using the expression 0.5 into 1 plus ZW2 divided by B. Now since the value of ZW2 is 2.8, which is greater than the width of the footing, when this is the scenario, there will be no effect of water table on the bearing capacity, which means the correction factor RW2 will also be equal to 1. We will substitute all the details in the above equation. So since the first term will again become 0, as this is the case of sandy soil, we'll substitute the values and on solving we'll get the value of the ultimate bearing capacity as 1546.9 kilonewton per meter square. Now we'll look up to the next case where the water table is 1.2 meter below the base of the footing. So again, as per Terzaghi's theory, the equation will be written for the ultimate bearing capacity, that is C into NC plus gamma into dF into NQ into RW1 plus 0.5 into gamma into B into N gamma into RW2. In this case again, the first term C into NC will be considered as 0. Now in the next scenario, the water table is exactly at the base of the footing. So here ZW1 value and ZW2 value is to be considered. So in this case, again RW1 value will be considered as 1 because water table is exactly at the base of the footing, and the soil above the base of the footing has no influence of the water table. So that's why RW1 value will be considered as 1, and RW2 value will be considered as 0.5 because the water table is exactly at the base of the footing. Okay, so ZW term becomes 0 and RW2 comes out as 0.5. So we'll substitute the values of all the variables available with us in the above equation, and we have to make sure in this that in the wedge term the value of the unit weight of the soil is to be considered as saturated, since all the soil below the base of the footing is under the influence of the water. So hence we have to consider the saturated unit weight of the water, and the the soil above the base of the footing is dry, so we'll be considering the dry unit weight. So taking all these possibilities on solving, we get the values of ultimate bearing capacity as 1248 kilonewton per meter square. Moving on to the third case, in which the water table is 2.5 meter below the ground surface. So again, as per Terzaghi's theory, we'll write down the equation. So in this case, we can see the water table is 2.5 meter below the ground surface. So ZW1 and ZW2 value will be found out. Okay, then in this case again we can see, since the water table is below the base of the footing, so there will be no effect on the soil above the base of the footing. So here also the value of RW1 will be taken as 1 because there will be no influence of the water table. But RW2 value, it will be found out. Now here ZW2 value is 1.3, which is lesser than the width of the footing. So in this case, when we substitute ZW2 as 1.3 in this given equation, the correction factor for the second term, that is the wedge term, comes out as 0.825. So we'll again make use of the Terzaghi's equation and we'll put all the values accordingly. Now we'll make sure that in the surcharge term, that is the middle term, the unit weight of the soil is to be considered as dry. But as we can see here, the wedge term, which is below, which represents the soil below the base of the footing, it will be having the influence of the saturated soil as well as the dry soil. So to compensate for that, we'll find out the gamma average value. So gamma average value is nothing but the weighted average of the soil, okay, available below the face of the footing. So that is calculated as 16.8 into 1.3, and the influence of the water table will be up to the depth of 2 meter, that is equal to the width of footing below the base of footing. So that is 0.7 meters. So 16.8 into 1.3 plus 19.5 into 0.7 divided by 1.3 plus 0.7. The value that will be getting us as is 17.75. This has to be used for the determination of bearing capacity, and it has to be substituted in the wedge term. So once we substitute all the variables that we have calculated, and we get the value of the ultimate bearing capacity of the soil for this corresponding condition as 1455.5 kilonewton per meter square. Now the fourth condition in which the water table is placed is 0.5 meter below the ground level. So again we'll be making use of the Terzaghi's theory and writing the equation that we have discussed in the previous slides. So in this case the ZW1 value is 0.5 and ZW2 value is to be not considered as the water is above the base of the footing. So in this case RW1 will be calculated and the value will be coming out as 0.708 as the value of ZW1 is lesser than the depth of the footing, and RW2 value is to be considered as 0.5, means water table is above the base of the footing. Now we'll make use of the equation proposed by Terzaghi, but in this case now for the surcharge term we'll make use of the gamma average, that is the weighted average of the soils, because we have dry soil as well as saturated soil present here, and for the wedge term we will be considering only the saturated unit weight of the soil. So the average unit weight for the soil above the base of the footing will be calculated as 16.8 into 0.5 plus 19.5 into 0.7 divided by 0.5 plus 0.7, which comes out as 18.38 kilonewton per meter cube. Substituting all these values that we have calculated and provided to us, the value for ultimate bearing capacity for this condition comes out as 1060 kilonewton per meter square. In the last case, in which the water table is exactly at the ground level, again we'll make use of the Terzaghi's theory, but in this case the value of the RW1 and RW2, that is the correction factors, will be equal to 0.5 because the water table is exactly at the ground level, and in the equation of the Terzaghi's bearing capacity the unit weight for both the surcharge term as well as the wedge term will be considered as saturated unit weight. So we'll substitute the values accordingly in the equation, and on solving we'll get the value of ultimate bearing capacity as 897.78 kilonewton per meter square. So that's all from this video. Thanks for watching.